Let's begin. Can you do me a favor, please, Ollie? Can you read the title? It says Lesson 2, what? Impulse in English means acting without thinking if you're impulsive. In physics, it has a very specific meaning. Impulse, and this you'll have to memorize, is defined as, don't write this down, don't write this down, don't write this down. It's defined as change in momentum. Now that's the English version of it. If you want to, in a second, I'll let you write that down. However, Jess, top left corner of my formula sheet, I have an abbrev for change in, do I not? What? That's my way of saying all of you are looking at the top left corner of your formula sheet. You have your formula sheet out in front of you. What's the abbrev for change in? Except we don't say triangle, we say something that starts with letter D. There's a, okay, we call it delta. So we can write this as delta. And what letter did you say was my abbrev for momentum? You can write one or both of those if you want. But impulse is defined as change in momentum. If I'm asking you to find the impulse, I'm asking you to find the change in momentum. What's the change in momentum? The impulse. And going back to you, Jess, what's change in anything from the top left corner? This is going to be your line for today, by the way. What's change in anything from the top left corner? It says triangle equal, change in equals delta equals what? Loud and proud again, so my little microphone picks it up. Change in anything is final minus initial, okay? So the first way I can think about this is if I know the final momentum, if I know the initial momentum, it's going to be the final momentum minus the initial momentum because that's change in anything. But we're going to go a little bit past that. It says, fill in the steps below to find the impulse equation. What we're trying to derive, if you're wondering, is that second equation right next to where it says P equals mv, the one that has a bunch of triangles in it, that one that has kind of three equations in one. So first of all, we're going to start with F equals ma, and we're going to get the a by itself. Oh, it was Ryan's theorem, wasn't it? Ryan, get the a by itself, please. Your theorem. We named it after you. We have F equals ma. Get the a by itself. Tell me what to write. So what does a equal? I'm going to have you repeat that, not to make fun of you, but to make a point. What does a equal? What does a equal? Put a pin in that, everybody. However, we've learned other expressions for acceleration. Sadie, if we had VF equals VI plus AT, remember that from way back when? Get that A by itself. How do you do that one? Would you add the VI? So what does A equal? VF minus VI over T. What does A equal? What does A equal, Ryan? No, yours. That's your line. What does A equal? What does A equal? If they both equal A, they equal each other. Yes? That's what we're going to do in our next line. We're going to say, you know what? Force divided by mass, where force is a vector, is the same as V final minus V initial divided by time. Jess, can you read me the top of the right-hand side here? Just read that to me. Except instead of F, can you say the word that F is an abbrev for? And can you say the word that I is? Hey, what is final minus initial the same as? I knew you'd get it. What? So above this, you can think of that as a delta V, a change in velocity. This is technically the impulse equation here, but it's got fractions and we don't like that. We're going to rewrite this with no fractions. Dividing by m on the left, Eveluna, how could I move the m over to this side? What's the opposite of dividing by m? And what's the opposite of dividing by t on the right-hand side? Multiplying by t on the left-hand side. And so on the next page, this is really what we're thinking to ourselves. Force times the change in time equals m times the change in velocity. And if I put that all together, because at the very beginning I said impulse is change in momentum. This is really the equation I think you have on your formula sheet. It says change in momentum, impulse, can be calculated by going, is it F delta T first or M delta V first? I had to give my formula sheet away, so which one did I write first? M delta V, force times change in time. This is massively abbreviated because what did you say change in anything was? So this can be written as final momentum minus initial momentum. Middle one can be written, what did you say change in anything was? You just said it. I'm having you repeat it for. And by the way, it is strangely, weirdly hard to say final minus initial. Everybody at least once says the finest minus. I don't know why, but I do the same thing. So final minus initial. This can be broken up into MV final minus MV initial. The day before the test, which is not going to be for quite a while, if you can't visualize this as that, and if you can't visualize this as that, you can add that to your formula sheet, but I'm going to discourage you from doing it now, because if you do it now, you'll never internalize it. You'll just always have that crutch, and you might not need the crutch. So the impulse equation says, if you want to find the impulse or the change in momentum, you can find it by going mass times the change in velocity, but on my calculator, I would usually go mv final minus mv initial because that's quicker to type. And you can also find it by going the force times the change in time. I don't know if you remember, I said near the beginning of the year, time has always been a change in. We've gotten sloppy and stopped writing the delta, but it's always a final minus initial. It's how you measure time. What's the final time you stopped? What's the initial time you started? That's the time. And so we stopped writing the delta. I'm putting them in here just for symmetry, so there's a change in everything to let you know this is a change in. Let me be even more basic. Your momentum is changing when your mass is changing or your velocity is changing. We're not going to look at the situation where the mass is changing. We're going to be looking at the situation where the velocity is changing. If your velocity is changing, what are you doing? If you're speeding up or slowing down, we have a special word for that. It starts with letter A. You're accelerating means there's an unbalanced force, which is why you also can think of it as the unbalanced force times how long you're pushing for. That'll change your momentum. I'm a Star Trek fan. Star Wars, meh. Soundtrack for Star Wars was great, but the science is terrible. Star Trek, they at least cared about the science. They got the vocabulary right. If you ever watch Star Trek, they'll talk about turning on the Enterprise's impulse engines. They'll say impulse engines full ahead. You know what they're doing? They're changing the Enterprise's velocity. They use the terminology correctly. Thank you, Star Trek. I wrote here, you can see this is kind of three equations in one. We never use all three at once. We use two at once at most. You may also have noticed I've been a bit more meticulous with my vector notation. This is because in momentum problems, there are often changes in direction. And what that's going to mean, Tamana, is we're going to have to let one way be positive and one way be. Okay? Doesn't matter which way you choose, as long as you're consistent for your whole question. In fact, let's look at one right now, next page over. Let's look at the baseball getting hit. Nikki, a baseball is pitched horizontally due east at 38 meters per second. After it's hit by a bat, it moves horizontally due west at 55 meters per second. Nikki, what is A asking me to find? So the first thing that I would write is my abbrev for impulse, which is change in momentum. And all of us are looking at that second equation on our formula sheet, that three equations in one. And we're going to try and figure out what we're going to use. One version of that equation has a force and a time. Look at the information that they gave me. Do you see a force in newtons at all or a time in seconds at all, Nikki? No. No. What do you see? I got a mass, and I see an initial and a final velocity. But now I have to focus on key words. Nikki, what word is this here? What word is this here? Is there a change in direction? Say yes. I have to let one way be positive, Tamana, and one way be. That's going to be your line for a little bit as well. What do you want to let be positive? What do you want to let be negative? I don't care. Pick. East is positive. It's been funny. It's been a 50-50 split. Some of my classes have let West be positive. Some have let East be positive. Doesn't matter. Fill in, all of you, the following phrase. Lazy but. All of you, fill in the following phrase. Lazy but. I've said that a bunch. So this is Mr. Dueck's. I want to be freakishly organized so I don't make a silly mistake and miss out on a negative, but I don't want to write a whole bunch. What did you say East is going to be? Pause. So here's what I would do, everybody. In front of the word East, put a plus sign, and anything that is East gets a plus sign in front of it. Make it big and stupid obvious. What am I going to put in front of the word West, do you think, Nikki? And anything that is West gets a big negative in front of it. That's usually enough for me to see what's going on. Okay. I think I'm going to use, write the equal sign, but don't write this next bit down. You've identified they gave me a mass and velocities. Don't write this down. Don't write this down. I'm going to use this version, except what's changing anything? Sorry, I got you mid-beverage there. So I'm not going to write that. I'm going to write MV final minus MV initial. That's what I've considered unabbreviating on the formula sheet, but clue in, if I get a chance to abbreviate, I'm going to abbreviate. We're good. Time to write out the numbers and then crunch. It's 0.144. Nikki, what's my final velocity? Oh, Nikki, you let me down. I made it red and everything. It's not 55. How can it can't be 55? Folks, help them out. What is it? It's negative 55. I'm kind of glad you did that because now no one will make that, and I'll call it dumb mistake because we wrote it pretty boldly there. Glad you did that. It's out of our system. Minus 0.144, positive 38. By the way, if my final answer is negative, West. If my final answer is positive, East, based on Nikki's frame of reference. Crunch the numbers, go to your calculator, and you want to keep this number on your calculator. Of course, by now you have your calculator out without me having to remind you to get your calculator out, since I'd remind. Oh, it is your. Okay, you got it out. Worried for a second there. Let's see. It's going to be 0.144 times negative 55 minus 0.144 times positive 38. Nikki, did you get negative 13.392? I'm going to write negative 13.4, but I'm going to store this on my calculator as I've showed you the trick, right? So negative 13.4. Nikki, units. It's right in what I wrote. Kilogram. Mr. Dueck, what if I forget? Look, look, look. I put the units next to the numbers, so you better be able to figure out the units. Yeah, kilogram meters per second. What if I had said, give this to me as a direction? Well, then you would write positive 13.4 kilogram meters per second at, what's our direction? West. I would take either of those. If it was a multiple choice question, I would give you either one of those, but not both, because then there'd be two correct answers. The only thing I'd be fussy on is don't say negative West, because I would argue negative West is probably East. All right. Don't overcomplicate this, folks. Be Captain Obvious. Where do you think the baseball gets its impulse from? It's another word that starts with letter B. Yeah. Let's visualize this. Sorry for those of you watching on YouTube, but I'll keep the recording going. So here's the baseball coming in. What direction was it traveling initially? East. East is that way. It's coming in at 38. Which direction did it end up going? And faster. So here's the change in momentum. First of all, the bat had to bring it to a stop. That was a big change in momentum. And then it had to give it the mass times 50, going in that direction. There's a pretty big change in momentum, but it's definitely all to the west. This makes sense for my visualization. One of the nice things about the impulse equation, Martin, it's a nice shortcut. You can actually pretty much survive without that little equation on your formula sheet, but you can turn 5 lines into 2 lines or 1 line with a bit of cleverness. And so I'm good with that. Martin, what's C asking me to find? Okay, don't write this down, don't write this down, don't write this down. I will give you full marks if you go, don't write this down. Everybody, F equals what? Don't write that down. And then you could say, well, I know the mass, A equals question mark. Did they give us a VF? Did they give us a VI? And in part C, did they give me a time? You could go VF equals negative 55. Don't write this down. You could go VI equals 38. You could go T equals 0.8, whatever the heck. Oh, that's not meters per second. That's MS, whatever the heck that is. You could use, what's A equal to? What, this was your line. Yeah, VI. And, okay, and in about 3 lines, you'll have it. And I will give you full credit if you do it that way. But you didn't write that down. Martin, we're going to write this down. What did they ask us to find? What did we find in part B? Sorry, part A. No, we did not find momentum. There's a word that starts with letter I guarantee it. In part, what? Which is not momentum. Change in momentum, yes, but it is not, I got to freak out a little bit. It's not the same as momentum. They asked us to find the impulse. They asked us to find, write this down, folks, that. Hey, Martin, is there a version of that that has a force in it? What? Get the F by itself. How would I move the delta T over? And 1 line, and I've already got the force. Force is impulse divided by time. I lied to you last unit when I told you Newton's second law was F equals what, ma. Actually, Newton was much more interested in impulse. That's how he wrote Newton's second law, as the impulse divided by the time. Now that simplifies, if you play around with it, Daniel, to ma. It does. But why is this so nice? Martin, what's the impulse? Negative 13. You know what? Actually, we could even go like this. Haha. Answer button divided by, what's the time? I gave it to you a bit weirdly. What does it say the time was? 0.8. What's that M in front? Now I'm trying to sneak in as much review as I can. What's that M in front? It's a metric prefix. On the back of your formula sheet where you have all the metric prefixes, what's lowercase m and abbrev for when it's in front of a unit? That's milliseconds. Stop, go look back. Milli, 10 to the what? You don't have to memorize it because I gave you the chart. Okay, so I'll start sneaking in some unit conversion. I'll start sneaking in some review. So the bottom is going to be 0.8 times 10 to the negative 3. You can probably use your scientific notation button, but you may or may not have to put the denominator in brackets. I don't know. It depends on your particular calculator model. But I can certainly go answer button divided by bracket 0.8 scientific notation negative 3. Martin, what'd you get? No, you can't. There's no way you got that. Did you not get a negative answer? I'm sure you got a negative answer. Yes? Well, that's not what you read. Don't you have negative 16,740? What's the negative saying? Let's write that down. Direction. Yeah. 16,740 newtons west. I would accept the negative. I would accept positive with the word west. But if you just wrote the positive, no, you've told me east. Now again, visualize the baseball coming in. Of course the force is to the west because it's got to first of all bring it to a stop and then get it going. These numbers here I made up. They're pretty close to major league numbers. What was VI? I've scrolled down. Nikki, what was VI? That's around 85, 90 miles an hour. This is at least a college pitcher, maybe even major league pitcher coming in. What was VF? That's over 100 miles. This is Aaron Judge pounding a home run out. So this is big force. Aaron Judge can put 16, 17, 18, 20,000 newtons into his baseball bat. Most of you on a good day would be about 5,000 newtons. This is major league numbers here. Oh, Jacoby, what's D asking me to find? I would have no problem if you used what Sadie said, A equals VF minus VI over T. But what did we find in part C? Ryan's theorem. It's going to be answer button divided by 0.144. Is that what it was? See if you can be a little better than Martin. What's the answer? Yeah, it's negative because, of course, the acceleration is to the west as well, and you let west be negative. It's going to be a big acceleration. Negative 116,250 or something like that meters per second squared, or 116,250 meters per second squared to the west. So this is weird. I could have done all of this with F equals MA and VF equals VI plus AT, but it would have been 3 or 4 lines instead of 1. Momentum and impulse, which are not the same thing, momentum and change in momentum, are our best tools for analyzing collisions. We'll look at car crashes, but in sports, tackling and body checking are collisions. Now, we have a bit of a limitation both for our car crashes and for our tackles. They're going to have to be head on. In real life, car crashes and especially tackles, they're often hitting from an angle. In Physics 12, I teach you vector mathematics, and we'll look at how to deal with angles. I'm not going to get into that now. So 2A says, what's the momentum of a 112 kilogram football player running due north with a speed of 3.6 meters per second? Okay, we can handle this. Who did I pick up? Claire. Momentum. What's our equation for momentum? By the way, Martin, this is momentum, not impulse. This is not change in, not delta P. This is just momentum. What's our equation? You read this earlier, which is why I came back to you. Yep. What's the mass? What's the velocity? And you've also, by saying that, you've just decided to put a plus sign in front of the word north and a plus sign in front of the 3 points. You've decided north is positive. Okay, that's fine. Everybody go to your calculator. What do you get? How much momentum does this football player have? 400 something. Yes? He's a little more than 400, I think. 403.2 units. Of course, it's kilogram meters per second. And if they had asked for a direction, I would say north. So this football player is running north. What if I'm a football player who wants to bring this person to a stop? B. What impulse? Oh, this is going to be impulse change in momentum. What impulse must a tackler impart to the football player to bring him to a stop? Eveluna, what's B asking me to find? And everybody underline the word stop, because that's going to be key to this. First thing I'm going to write is our abbrev for impulse. What did I find in part A, Claire? I found P. Delta, what's change in anything? I think I can get away with going, this is going to be the final momentum minus the initial momentum. Eveluna, what's the final momentum if they're stopped exactly as a number? What was the initial momentum? Answer button. You know what? You could probably do this in your head without a calculator. You know what 0 take away 403.2 is? Just what? Negative. So what's the negative 403.2 kilogram meters per second saying? It's saying if this guy is running north with 403.2 kilogram meters per second and I tackle him, I better have a momentum south of 403.2 kilogram meters per second south. I need to cancel his out. Now, there's a couple of ways I can do that. Claire, back to you. Momentum is what times what? Okay. If I'm heavier than 112 kilograms, I don't have to be moving as fast. If I'm lighter, I have to be moving faster. We've just explained why, if you watch football, why the mass players stand where they do. Where the heaviest players all stand, right near the line. They don't have to get up much speed, but they've got enough mass. They've got more M in the MV. They can cancel out your MV. Where do the smaller players have to start? Further back, because they've got to build up a head of steam to make sure that they've got enough momentum to bring this person to a stop. Is that all right? C. Lachlan, what's C asking me to find? I could go F equals what? And then I could go A equals VF minus VI. I got all that information there. But what did I just find in part B? There is a version of impulse. There's a version of this equation that has force in it. From your formula sheet, which version of this has force in it? Okay, so you know where we are. We're in the momentum section, right? Don't be reading me P equals mv. We're in the equation next to it, that 3 equations in one. One of those has a force in it, I guarantee it. You got it. Yep. Yes. Yes. Get the F by itself. What's the delta T doing to the F? Adding, subtracting, multiplying, or dividing? So, one line. The force is going to be my answer button divided by how much time did they give me in this question, Lachlan? Martin, you're going to tell me the answer, and you're going to tell me the answer carefully this time. No, that's impossible. That can't be that. There's got to be a negative on your calculator right now, is there not? This was negative. Divided by 0.8. Got a negative. Or did you not do this one? Okay, well, that's what you should, right? Answer, but it's going to be negative 403.2 divided by point. It is negative, yes? What's the negative telling me? What direction must the force be applied? Yeah, because you let north be, I think you were the first one I picked on. You did A? No, who did A? You let north be positive. Okay, so it's going to be negative. What's the answer? 504? Is that right? Negative 504 newtons? Or 504 newtons south. Okay, before we go further, Lachlan, look where the T is, the time. Is it on the top or on the bottom? If time gets bigger, what would happen to this answer on our calculator? Okay, if I'm a big lumbering lineman and I wrap up this guy, but it takes me 1.2 seconds to bring him to a stop, I will still have stopped him, didn't hurt him as much, not as much force. If I'm a smaller guy who hits him while sprinting and blows my shoulder through him, and so the time of impact is only 0.3 seconds, I've nailed him with a much bigger force to bring him to a stop. Oh, and by the way, I felt the same force because forces come in, but ideally I'm taking it on my shoulder pad. He's taking it on his chest. And now we're explaining what makes a big hit, what makes a good tackle, but not a big hit. Nice tackle, wrapped him up, they'll say, but it wasn't like you ran through him. Big hit, they'll say, shorter time. Same impulse required. This right here, Ev, this is the car accident safety equation. Because in a car crash, we're stuck with certain variables. What's the final velocity of every car crash ever? Zero. What's the final momentum then of every car crash ever? Zero, because mass times velocity. The initial is going to be whatever the mass times the speed limit is. If I can somehow make the crash last longer, the force goes down. F equals what? Does your mass change in a car crash? No, but I can change your acceleration. If I can make the acceleration smaller by making the time larger, more survive. What kills people in a car crash is not speed, it's not force, it's acceleration. I wrote here, although we solved the previous problem using impulse, we really could have done it using Newton's second law, F equals ma and Vf equals Vi plus At. And I will give you full credit if that's your comfort area and you know you can get it right. I want to emphasize, Brooklyn, I'll give you full credit if you do it that way. So, but why am I bothering with momentum and impulse? Next lesson, you'll see it's our best tool for analyzing car crashes, especially when there's more than one object. But we can even answer something like this. Next page. Suppose we have two eggs, and let's make them identical eggs. They're clones of each other. Same size, same shape, same shell thickness, same everything. And we drop them at the same time from the same height. One lands on a cement floor and breaks, split, and one lands in a bucket of water and survives. Why does the one survive in the bucket of water? Why does the one that lands in the bucket of water survive? Rant about it about 2 minutes ago. Okay. Let's see if we can puzzle our way there. Let's see if we can visualize this. First thing I want you to notice is, are they getting dropped the same height? So when they hit the ground, their initial impact velocity will be the same, yes? What will their final velocity be after impact for both of them? Okay. So if they have the same final velocity and they have the same initial velocity, I'm going to say this. First of all, here's the cement. Draw a line down the middle of the page. Here's the water. I'll abbreviate water with H2O. I'm going to start out by arguing they all go through the same impulse. Why does the egg survive then if they have the same change in momentum? Yeah. Okay, give me the version of impulse that has a T in it, please. It doesn't say F equals, delta P equals. Give me the version on your formula sheet. There's one version that has a T in it and another letter. Yes, yes. Okay. Impulse is force times time. So for the water, we have really big time, doesn't need much force. For the cement, really small time, well, to get the same impulse, you have to have a really big force. That's the only way you could get matching numbers. That right there is our complete understanding of keeping people alive in car crashes. We want the one on the right. How do we do that in car crashes? Well, we have crumple zones. Those are all designed to make the car crash last a bit longer. Airbags. Has anybody been in a car crash where an airbag deployed? Okay. You have been? Okay. If you see a commercial that a car company runs and they show the airbag deploying, they will never show it in real time. They show it in super slow motion and it looks so gentle. You see a pillow unfolding in front of your face. And oh, I can just take a nap on that pillow. Airbags are not gentle. They're like getting punched in the face. Yeah, you're not. You've had a. Oh yeah, oh yeah. You'll break your nose, but you'll survive. By the way, the main reason cars have airbags here in Canada is because Americans don't wear seatbelts. In Canada, we passed a federal seatbelt law. Boy, I think in 1975, 76, a long time ago. You guys have grown up to the point where you feel uncomfortable when you're not wearing a seatbelt. In the US, it's a state by state law, and some states, freedom, we can't make us wear our seatbelts, so they have never been able to pass a seatbelt law. So, airbags, which are expensive and finicky and a waste of money if you're wearing a seatbelt. What else do we do? You may have seen it on the Pitt Bridge. Have you noticed what's in front of the cement barriers? I think they're still there. I haven't looked lately. They have these big yellow barrels full of water. It's cheap. Big plastic garbage pails full of water. So instead of it's going to be boom, 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 slowly slowing you down. And again, the nice thing is, because if you're impacting a brick wall, the time is so small, it's not that hard to make the time from crazy small to maybe 4 times bigger. You've just reduced the force by 1/4. I had a cars in the 60s and 70s, they were designed to be indestructible. In a car accident, the car wouldn't even feel the force. Nothing would get damaged. Where would all the force get transmitted to then? Yeah, the passengers. And car companies thought that's what people wanted. In the 80s, car companies started to realize parents would rather have live kids, broken car, than pristine car, dead kids. Took a while. Car companies are kind of stupid that way. But nowadays, cars are designed to have way more damage because all of that is less force getting transmitted to you. Is that okay? You okay with the big F little t as kind of my graphics? You could write a longer description if you want, but I'll use that as an abbrev quite often to show what's big and what's small. Mr. Dueck needs to pummel someone. Yes, he does. We're going to pause for a second here. Sorry, those of you on YouTube. Oh, I hit the wrong button, Mr. Dueck. Hang on. Let's go like this. So YouTube, sorry, I pummeled a kid. But it was for science. So if you're wondering what's the rule for car crashes, injuries are not caused by speed. They're not caused by force. They're caused by acceleration. And if I can make the acceleration smaller by making the time larger, damage from change in momentum isn't caused by how much momentum is absorbed. It's caused by how fast you absorb the momentum. If you can make time longer, you're going to be fine. All of you have gone from 100 kilometers per hour to 0 all the time. When? Leaving the freeway, right? Take an off ramp, you slow down a little bit. You head onto the low heat, now you're doing 80. You turn into your subdivision, you slow down a little bit, now you're doing 60 or 50. You get into a crowded subdivision, now you slow down a bit, now you're doing 30. You pull to your driveway, now you're doing 20. But you spread out over so much time, you don't even notice it. You don't have to brace yourself, nothing. Example 4, here's another way to think about the egg question. Why do they use bales of hay to line some racetracks, especially motorcycle racetracks? What do the bales of hay do? But so does a brick, also slows you down. Smoother isn't the physics word. Which variable are they changing? I've been going on a rant. What? Okay, again, here's what I said. With a bale of hay, T gets bigger, F gets smaller. With a brick wall, time gets smaller, F gets bigger. Yeah. In many sports that involve striking something, tennis, baseball, soccer, golf, players are told to follow through when they make impact. Why would following through help the ball to leave with a greater velocity? How would that make it a bigger force? No, it doesn't make it a bigger force. I like what you're thinking, though. So here's, by the way, when you're hitting a ball, what you're really doing is you're giving it some impulse, a change in momentum. So let's write that down. And let's write the force times time. Mason, let's suppose you've lifted weights and you've practiced. You can't get the force any bigger. What other variable is there on that side of the equation? When you follow through, you're impacting for longer, which means as time goes up, V final is going to go up because final minus initial. The final is going to be bigger. In fact, the opposite is true as well. If any of you play tennis, to do a drop shot, what you do right when you impact the ball, you pull away. You want the time to be so tiny that the ball just comes to a stop and blips over the net instead of having it go back to the player. Or when you're bunting and when you're playing baseball, what do? You pull back right at impact. You're trying to just bloop the ball down and have it roll a little bit so that the players have to come scrambling for it. You don't want to give it so much momentum, so much impulse, change of momentum that it makes it to the base, the guy on the base. You want it to be somewhere in the middle. You got to come scrambling. It's all about making time smaller. So the opposite of that. What has more momentum? A 1,000 kilogram car moving at 100 kilometers per hour or a 200 kilogram truck moving at 50 kilometers per hour? Your hint is it's a trick question. What did you suggest? Which one has more momentum? It's a trick question. The same. The units suck. I'd have to convert them. But look, twice as fast, half the mass. Half as fast, twice the mass. It's the same. What does that mean? If they had a head-on collision, their momentums would cancel out exactly. They would go like this. There wouldn't be anyone going that way or that way. Their momentums would exactly cancel out. Does a moving object have momentum? Yes or no? Well, how do you calculate momentum, Claire? This is your line. Does a moving object have mass? Does a moving object have velocity? Does a moving object have momentum? Because MV. Okay. Turn the page. Follow-up question. Does a moving object have impulse? What's impulse? The very first line from this lesson. What's impulse? Thank you for somebody being clever enough to go look at the very first line of the lesson. A change in momentum. Does a moving object have a changing momentum? Only if what? Speeding up or slowing down. Only if it's accelerating. In fact, you know what? Only if there's an unbalanced force. That's why one way to think about impulse is a force times a time. So does a moving object have impulse? Only if, what's A and abbrev for? In physics, what do we use it all year? Okay, only if accelerating. And remember, accelerating can mean speeding up or slowing down in physics. So just because you have momentum doesn't mean you have impulse. But certainly if you have an impulse changing momentum, then you have some momentum until you come to a stop. Two more. When you jump from your lab table to the ground, why do you bend your knees as you land? Time gets bigger, force gets smaller. Watch a toddler who's just learning how to walk, and especially if they're holding mommy and daddy's hand, one of the things they love doing when they come to a curb, they think they're very brave. They'll jump off the curb onto the pavement. But watch how they land. They land stiff and awkward. They haven't yet learned that because they've just learned how to walk. Watch them when they're 4 years old. By that time, they've had some playground time. Now when they jump and they land, you see they've learned to bend their knees. They've learned increased time. Doesn't hurt. Sorry, that F is right on the line. You can't tell that's an F, Mr. Dueck. Let's erase that. F. Make that a better F, Mr. Dueck. There we go. Okay. Which of the following situations is more likely to knock out a boxer? Leaning back while taking a punch or leaning in while taking a punch? Leaning in. Why? Smaller time, bigger force. Because what the boxer's face is doing is applying an impulse to the fist, bringing the fist to a stop. Smaller time, bigger force required, and forces come in pairs, bigger force on the face. In fact, if you talk to a boxer, they'll say, oh, I caught him coming in. What that means is they KO'd the guy. They got him just right. Now, as always, I'm really simplifying things. Boxing is much more complicated than that. But yeah, that's much more likely to knock out a boxer. This is also the physics, if any of you are doing martial arts, this is the physics of trying to split a board. What your final momentum is going to be is 0. Your initial momentum is going to be however fast you can swing your hand. You want to have the time as small as possible to get the force as big as possible to break the board. What's your homework? You can cross out number 6. But you can do the rest. There's about 14 minutes left. You can probably get it done in class. Let me just stop this.